Hello guys, let's start. So it is lecture 7.1, linear maps. In abstract algebra, it is very ordinary situation when we consider some abstract objects like vector spaces or like rings, fields, groups, something like that. But so imagine these guys are rings, for instance. And then usually we study not just one of them, but a lot of them simultaneously. And it is very important to understand how two abstract objects talk to each other. So basically, some sort of maps between abstract objects, things like that, are usually very important. So even in sets, so if we talk about sets, if you have a set A and set B, then very first important idea related to sets is the notion of a map between sets, and then you can take compositions of these maps and things like that, and this is all very important. So there is a general area of mathematics which is called category theory. It studies this sort of abstract objects in their social behavior with respect to the same species. The main idea there, again, is that you not only study objects, but mainly you study maps between them of some sort. So today I'm going to introduce a notion of linear map. A linear map is a map between two vector spaces. So basically for a pair of vector spaces, we will introduce a notion of a linear map between them, which will be some map of these sets of vectors satisfying some simple properties. And the main idea is that basically, if you take just one vector space, it is boring. All vector spaces of the same dimension are the same, they are isomorphic. But when you try to look at a vector space and understand all the ways it is related to other vector spaces, that makes them interesting. So basically, you can think of linear algebra as a science studying more linear maps than vector spaces. It is much more accurate. So, and in the next lecture, lecture 8, we will understand that actually matrices are a very concrete down-to-earth way to write down linear maps. So all algebra of matrices we talked about last time will be explained and understood in the next lecture from this perspective. Okay, so this was some silly introduction. So let's go into more details. Let me define what is a linear map. Okay, so here is a definition. So let V1, V2 be vector spaces over the same field F. It is very important that we take two vector spaces over the same field. Field is fixed, like real numbers, complex numbers. It is possible, but much more requires for much more care if you want to get vector spaces over different fields. Anyways, so let's assume V1 and V2 are vector spaces over the same field F, and then a linear map L from V1 to V2 is a map. So map is the same as function. Sometimes people say function. So this is just something which associates to every element here, an element there, such that two properties hold. So firstly, for every two vectors, V and W in V1, L of V plus W equals L of V plus L of W. So it sends sum of vectors to the sum of vectors, and second is that for every scalar in the field, L of lambda V equals to lambda L of V. So if you rescale the vector, the image is also rescaled, and of course, one can see that 1 and 2 implies that, for instance, L of 0 is equal to 0, or L of, say, V minus W equals to L of V minus L of W. And moreover, if you have any linear combination, x1 v1 plus and so on plus xn vn, it equals to x1 L of v1 plus and so on plus xn L of vn. So basically, if you have a linear map, when it eats a huge crocodile made out of a bunch of vectors with a bunch of scalars, it spills out this vectors, image of L in this vectors times the same scalars. So it respects this linear combination business. So sum to sum and product on number on the product on the number. So this is what a linear map is, and as you see, definition is very simple. So let me give you several examples. So actually there will be tons of examples, so let me just do something. For instance, just the most naive example. For instance, you take R2 and you want to write down a map to R2. So you can take a pair of vectors, say x, y, and send it to x plus y, y. And then you can easily check that if you, for instance, so this is L. If you, for instance, take L of x1, y1 plus x2, y2, so on one hand it equals to x1, so this is the same as L of x1 plus x2, y1 plus y2, and then so this one equals to, according to this formula, x1 plus x2 plus y1 plus y2, y1 plus y2, and then this is the same as sum of x1, I'm totally lost, x1 plus y1, y2 plus x2 plus y1 plus y2, sorry, y1 plus y2, y2, and this is literally the same as L of the sum. So in this way you can check it directly. So geometrically that's a beautiful map. So what you do, you take your plane, and then for every point, y coordinate is fixed. So basically points move along these lines. Line y equal to 0 is fixed, and then everything is kind of moved. So this, for instance, square will move here. So it is like a, it's called usually a boost, I guess. So all rectangles go to parallelograms. So this is what it is doing. Okay, so that's an example of an interesting, beautiful linear map. So second example is just a very simple example. So if you take V and you can take L to any other, like V1 to V2, and for every vector V in V1, you just put L of V equal to 0. So you can just send all vectors to 0 in there, and there is basically nothing to check. So this is the most boring map, so usually you will just call this 0 map. Honestly, vector maps between vector spaces form a vector space themselves, and this will be 0 there, but we will think about it later. So this is another example. Third example, let's take as a vector space the vector space of polynomials over some field, and then there is a map from L from V to V, which takes a polynomial and takes a derivative. And then these two properties are just the fact that the derivative is linear, and when you multiply polynomial by a number, you can take it out of the derivative. So I don't even know for this example. For instance, you can take a vector space being n by n matrices over F, and L of a matrix takes the transposition. So if you flip the matrix, if you flip sum, it's the same as sum them, flip them, and sum them up, and you can check that this property also holds. So tons and tons of examples. Okay, so next maybe important example. So next example, so here is what one can do. So one can take as a vector space just this typical example of Fn, and then take some, and this will be V1 and V2 will be just F. So this is dimension n, this is dimension 1, and then if A1 up to An in F are some numbers, then one can define L from V1 to V2, which takes x1, tuple x1 up to xn, and sends it to A1 x1 plus and so on, plus An to xn. So this is an example of a linear map, and again, if you take two tuples like that, you sum them up and you check that the vectors, the numbers you will get here will add. So this is an example of a linear map to vector space of dimension 1, and honestly all maps between Fn and F will be like that. Okay, perfect. So by the way, a bit later we will talk about isomorphisms, which we already mentioned before, and isomorphisms are very important examples of linear maps as well. So so now maybe one brief idea. So so remark. So if you have vector spaces V1, V2, and V3 are vector spaces over F, then if L1 is a linear map from V1 to V2, and L2 is a linear map from V2 to V3, then one can take their composition. So composition, remember, you take L2 composed with L1 from V1 to V3, because it takes a vector in V1, it eats it, first L1 eats it, it goes to V2, then L2 eats it, and then it goes to V3. So that's why you write the composition in the opposite direction, then you just say it. So this is a map from V1 to V3. So if these guys are linear, so these guys are linear, then this is also linear, Okay, so you can compose linear maps, and this is completely trivial. So if you just take L2 composed with L1 of a sum, I mean, I can just write it down. So L2 composed with L1 of a sum of vector V and W equals L2 applied to the sum L1V plus L1W equals to the sum L2 of L1 of V plus L2 of L1 of W. So as simple as that. And maybe this was one remark. And second remark is a very important remark, again, a little bit abstract. So if V is a vector space, then there is a very important linear map identity V from V to V. And what this map, so let me call it L, what it does for every vector V in the vector space V, L of V just equals to V. So it does not, it is just a rest map, so it does not do anything. Every vector stays where it is. And so this is an example of a linear map as well, and obviously sum goes to sum and so on. So, so maybe the fact that you can compose them, and the fact that there is this trivial map, and the fact that there was a zero map gives you some hint how they are related to matrices, because this will correspond to identity matrix, this will correspond to multiplication, and so on and so forth. But we will see it next time. Okay, what else? So what else do I want to say here? Okay, so next I want to formulate a very important theorem. So let me erase this part. Okay, so proposition. So very important one. 1 second. So let V be a vector space of dimension n, and W is some other vector space, maybe infinitely dimensional, so that's not important. Suppose E1 up to En inside V is a basis, and V1 and so on, Vn inside, let's say W1 up to Wn inside W are some vectors. So maybe even all equal to 0 or all the same or a basis, anything. So then there exists a unique map L from V to W. So when I say a map L from V to W, it's kind of obvious, I mean linear, so linear. Such that L of B1, L of E1 equals to V1, and so on, L of En equals to Vn. So what it tells us? It tells us that if you have a vector space, say, I don't know, R2, and you have here some basis, say your favorite two vectors, E1, E2, and then you have some other vector space, I don't even know, some complicated vector space, say like polynomials or anything else. So then if you want to find the linear maps from R2 there, what you need to do, you just need to figure out where you want to send E1 and where you want to send E2. So if you know that this one goes here, this one goes there, you don't know anything else, but you immediately will have a unique map. So basically, to know a map, it's the same thing as if you fix a basis, just to know where the basis vectors go. That specifies the map completely. And for every collection of n vectors, you can send any basis to this n vectors. If you start with a collection of vectors E1 up to n, which is not a basis, this will not work. It might happen that if there are some relations between them, this can go wrong. So you should be careful that you start with n vectors which form a basis. So proof. So proof will tell you immediately how to construct this map. So the proof is very simple. So first, let's start with uniqueness. So assume L1 and L2 from V to W are such that for every I less or equals than n, L1 of EI equals L2 of EI equals to Wi. So assume that there are two linear maps which have this property. Then for any vector V inside V, there exist x1 up to xn, some scalars, coordinates, such that V equals to x1 E1 plus and so on plus xn En. So we take any vector and write it down in a basis. And then we know that L1 of V equals to L1 of this linear combination. But then we can open brackets. So this is the same as x1, L1 of E1 plus and so on plus xn, L1 of En. So this is the same thing, and now we can just use that. So this is the same as x1. So we know that L1 of E1 is the same of EI is the same as L2 of EI. So it's the same as L2 E1 plus and so on plus xn L2 En. And this is the same as, according to the same logic. Now we, on the contrary, just plug in and plug in all xi's and then use it the sum, and we get L2 of x1 E1 plus and so on plus xn En, which is L2 of V. And we see that for any vector, L1 of V equals to L2 of V, so L1 equal to L2. So remember, if you want to say that two maps are equal, it's just the same as to say that they are equal on every vector. So you plug in any vector and you get the same thing. So that was the proof of uniqueness. And the second part is existence. So existence. So I need to construct such map, and then I would check that it is linear. So we need to construct a map with this property. So for every v inside v, there exists a unique set of coordinates x1 up to xn inside f, such that v equals to x1 e1 plus and so on plus xn en. So remember, for every vector there exists a unique set of coordinates x1 up to xn with this property, and then just define L of v to be equal to x1 w1 plus and so on plus xn wn. So we just put by force L of any vector to be equal to x1 times the image of the first vector up to xn times the image of the second vector. And then the claim is that L is linear. So claim is that L is linear. So let me check that. Okay, I will erase this part. Okay, so we need to check two properties. Let me. So one is that so suppose that we have a pair of vectors. So v1, v2 inside v, and we need to check. So the question is, what is L of v1 plus v2? So suppose v1 has coordinates xi, so it is the sum of xi ei from I equal to 1 to n, and v2 is the sum yi ei from 1 to n. So suppose one of them has coordinates xi and then the second has coordinates yi. So then we know that L of v1 is sum of xi wi, and L of v2 is sum of yi wi. So sometimes when people write down the summation signs and it is obvious that we sum from 1 to n, you just don't write that. That's sometimes helpful. So then v1 plus v2 of course is equal to sum. So when we sum up here we can take ei's out, so it's sum of xi plus yi ei. And so since coefficients of a vector are defined uniquely, so because this ei is a basis, if you know some presentation, it's unique. So then, according to our definition, L of v1 plus v2 equals to sum xi plus vi wi, and then if you just open brackets and use distributivity, it is the same as sum of xi wi plus sum of yi wi, which is the same as L of v1 plus L of v2. And this checks the linearity. And so this checks that L of sum is equal to the sum of values of L, and 2 is just similar. And this proves existence. Similar. And this is the end of the proof of the proposition. So again, we just constructed this map. You just take the same coordinates as your vector had, but instead of ei, you write down this wi's. So this is how you do it. Okay, by the way, the previous proposition of course works very well if your basis is infinite. So I just said that for a finite basis to be slightly like more down to earth. But for instance, if you have a vector space V, which is just a space of polynomials, then for instance, the idea is that if you want to define a linear map L such that for every n greater or equals than 0, L of x power n is n x power n minus 1, then L of every polynomial f of x, f p of x is just the derivative. So to know what is the derivative, you just need to know this map on monomials. And this is basically the idea of the previous theorem. Another example is that if you have this map L of xy being x plus yy. So this one is a unique map such that L of 1, 0 equals to 1, 0, and L of 0, 1 equals to 1, 1. So you can basically think of this linear map as defined by sending, in other terms, L of E1 equals to E1, and L of E2 equals E1 plus E2. So this is another way to think about this map. So this is a unique map with these two properties. Okay, so these are two examples. Now let me talk a little bit about how far linear maps are from injections, surjections, or bijections.